experiment found dark matter in the 1970s. And it's been 40 years, and we've just taken a 5-minute break, so we should have figured this out by now. What is dark matter? We have no idea. We have a lot of ideas, but we don't know. Okay, but let's start with a baseline. As good theorists, the first baseline null hypothesis that you start with is what's called the cold dark matter paradigm, which is the statement that dark matter is a massive particle. It only interacts with gravity. Full stop. Cold just means that it's slow enough to actually clump into galaxies. If it's too fast, then it starts flying apart. But this is just, it's a heavy thing that only interacts with gravity, and there's nothing more we can ever learn about it. This is, in fact, this is not a particle model. This is not something we can incorporate into our understanding of particle physics. So before we land here, we should exhaust the other possibilities that we can think about. Okay, so let's build a particle model. If the baseline is dark matter doesn't talk to us in a way that isn't gravity, our first guess should be dark matter does talk to us in a way that's not gravity. So our guess is dark matter talks to us, but weakly. Let's deconstruct the statement. By talk to us, I do mean in a way that is not gravity. And by weakly, I mean it is weak enough that we haven't immediately detected it. It's not actively glowing right here, but it's still way stronger than gravity. I'm talking about an interaction we can understand with particle physics. Okay, so if my guess is dark matter is a massive particle that interacts weakly, I'm going to call it a weakly interacting massive particle, or WIMP for short. So WIMP as a particle model, it talks to normal matter specifically in a weak way. These particle models are typically, WIMP models are typically a little bit heavier than a proton mass. A WIMP mass is roughly 100 times the mass of a proton, so roughly the mass of like a heavier chemical, like xenon. And when I say it couples weakly or interacts weakly with normal matter, I'm talking about 3 specific types of interactions. The first one is an interaction where a dark matter particle and a normal matter particle, they come in and they bounce off each other. It's a collision like rubber balls. And then the second type of interaction is one where dark matter particles can come in and normal particles come out. And the third type of interaction is one where normal particles can create dark matter particles. It's the opposite of the second one. And the rate of each of these processes is roughly proportional to the strength of this interaction. I've designated it as weak nebulously, and also the abundance of available materials. For the second one, for instance, it is proportional to how much dark matter we have to create normal matter with. But the fact that we can do this second interaction, and the fact that dark matter particles in this model are heavier than normal matter particles, and protons and neutrons, gives rise to a very interesting property that WIMPs have. So, this is a toy picture of the early universe. There are dark matter particles and there are normal matter particles. But the thing is, nature is very lazy and it prefers lighter particles. So if dark matter particles are heavy and normal matter particles are light, and there is a way to get from dark matter particles to normal matter particles, nature is going to try to make this conversion happen. Dark matter particles will become normal matter, and over time, there will be less dark matter and more normal matter. And if this scenario is allowed to continue, then we will end up with no dark matter. And that is, in fact, not what we see. And this is because we have overlooked a very important feature of the universe, as someone had mentioned earlier, the universe is expanding. And this just means that the average distance between each of these dark matter particles is growing. And so from each dark matter particle's point of view, its neighbors, its fellow dark matter particles are getting further and further away, and it's getting harder and harder for two of them to get together and make some normal particles. The rate of interaction is again proportional to the strength of the interaction times the amount of dark matter that is available to do this with. As the strength is not changing and the amount of available dark matter seems to be getting lower, this interaction rate is going lower and lower, and effectively it stops at some point. And we are left with the amount of dark matter that we see today. So this type of dark matter, a type of dark matter with this property is called a thermal relic. WIMPs are typically thermal relics. And this property is compelling because now we have a relationship between the amount of dark matter that we observe and the strength of its interaction to us. These two things are not obviously related, but in this type of mechanism, we can generate a prediction for how much dark matter there is based on what the model says about how strongly they interact. Okay, so we have, we said a lot about what WIMPs are like as a theorem. Now, theorist hat off, experimentalist hat on. How do we actually find these things? Well, now that we have a model, we can design experiments that specifically target a model, and then we can rule out or discover a specific type of dark matter. We want experiments that specifically look for the interactions that this dark matter has. And the guiding philosophy for designing this type of experiment, and in fact, all dark matter experiments, is we want to learn about the stuff that we can't see by looking at how it influences the stuff that we can. We did this thing with rotation curves. We couldn't see dark matter, but dark matter influenced stars gravitationally, and we looked at stars. So these are microscopic interactions. They're very different from the stellar gravity thing. But let's look at what each of these interactions look like. These are the three interactions again. But from a practical point of view, keeping in mind that dark matter is invisible, what do these interactions actually look like? If you take away your knowledge of what's happening in the dark matter side, this is what you see when you look at the normal matter. The first type of interaction looks like the normal stuff is getting bumped by nothing. The normal stuff comes in, something unknown bumps it, and then it comes out in a different direction. The second interaction just looks like normal stuff is coming out of nowhere. And the third interaction looks like normal stuff is disappearing into thin air. So these are the things that we can observe, and we design experiments to look for these specific things. So this first interaction, we want to look for normal stuff being bumped. And these interactions are very, very rare. We expect them to happen extremely rarely. So to design an experiment that can give us the best chance of detecting this type of dark matter, we want normal stuff that we can watch very, very closely. We want to minimize the chance that other unrelated normal stuff can bump it and cause it to be bumped. And we want to maximize the chance that dark matter can bump it. This type of method is called direct detection experiments. And they do pretty much exactly this. You get a bunch of really cold stuff and you put it in a vat. It's cold so that particles aren't moving around and bumping each other. And then you stick it underground. You stick it underground so that other particles can't easily get to it. You have a large amount of it, and you wait for a very long time to maximize the chance that dark matter comes along and bumps one of them. And then you see if anything bumps. For the second interaction where dark matter is creating normal matter, it looks like normal matter is coming out of nowhere. To find this, you want to go to a place with not a lot of normal stuff first, because there's a lot of normal stuff here and you don't know where it's coming from. You want to maximize the amount of available dark matter for this process. And you also want to minimize the chance that the observed normal stuff came from a normal process. So to do this, This type of experiment is called an indirect detection experiment. This is one of the examples. You launch a satellite into space, where it's a little bit emptier. You point your experiment directly at the center of the galaxy, the center of the gravitational potential, where there is the most dark matter, and you can maximize the amount of dark matter available for your normal matter generation. And you look for the weirdest type of normal stuff you can think of. You look for things that generally you don't expect to see from stellar astrophysics types of processes. Okay, and then for the third one, the one that looks like normal stuff disappearing into thin air. What you want to do is get a lot of normal stuff and try to make this process happen really hard. And then you want a way to precisely measure the amount of stuff that came in and the amount of stuff that came out so that you can see if any of it's disappeared. This is what collider experiments, like the big one in Switzerland, are trying to do. They accelerate a lot of normal stuff, they have big proton beams, and they smash it all together, trying to get them to create new stuff. And then they surround the entire thing with detectors so that they measure all the normal stuff that is coming out. So they know what's going in, and they know what's coming out that is normal stuff. They can figure out if anything's disappeared. And if things are consistently disappearing, we have good evidence of dark matter creation. So these are, so far, we've talked in a large amount of detail about this one particular model. It's very simple from where we started with. I just started with dark matter interacts with us, but kind of weakly. And from that, there's good theoretical motivation. There are other particle physics reasons why we might want WIMPs that I'm not really going to get into. And there's a good set of experimental things that we can look for. There's 3 very distinctive types of phenomena we can search for. For the crib sheet, it is typically about 100 times a proton mass, so it is on par with what normal particles, like normal chemicals, atoms and molecules weigh. It's a thermal relic, which means that, again, that there's a defined relationship between the amount of dark matter and the strength of its interaction, which is a very non-trivial fact. And then there are 3 main programs for experiments, which are the direct, indirect, and collider searches that